Everyone, my name is Rochelle Angel, and I'll be your host for today's webinar. It's a MapleSim eSymposium series, and it's called MapleSim Models Aid in Development of Training Simulator to Improve Labor Induction. I'm joined here today with Dr. James Andrew Smith, who is an assistant lecturer and graduate attribute lead of York University, and Graham Jackson, who's an engineering specialist here at MapleSoft. Before we get started, please note that you can use the chat window to contact me for help if you encounter any technical glitches during the webinar. You can access that window by clicking on the chat icon in the top right corner of the screen. If you're in full screen mode, then you'll need to navigate your cursor to the top of the screen to expand the WebEx toolbar to see the chat icon. Now, I'll pass the floor to Graham so he can begin today's webinar. Enjoy, everyone.
Thanks, Rochelle. So welcome, everyone, to the Research eSymposium series. I'm pleased to be joined today by Dr. James Andrew Smith, who is from the York University's Lassonde School of Engineering, and he'll be presenting today's presentation. But just before we get into that, I wanted to give you folks a quicker introduction to MapleSoft and why we provide support for projects like this. So MapleSoft has over 30 years experience in supporting advanced research projects. In fact, the company's core symbolic technology, the ability to allow computers to handle problems at the equation level instead of attempting to solve them purely numerically, this was developed as part of a research project in 1980 at the University of Waterloo in Ontario. So since then, many of our highly advanced computational technologies have had their beginnings in many of these research projects. We were founded in 1988 to commercialize these technologies through the development of the popular mathematics tool Maple and our powerful multi-research projects. We were founded in 1988 to commercialize these technologies through the development of the popular mathematics tool Maple and our powerful multi-domain simulation tool MapleSim. We're now a leading provider of high-performance tools and technologies for solving a myriad of technical problems in engineering, science, applied mathematics, all throughout the world. Our software and services touch hundreds of thousands of people worldwide, and we're well known for our expertise in mathematical and system-level modeling and analysis. And at the base of it, we acknowledge we can only really advance through the support of engineering research projects that require our technologies, and have been recognized as a powerful partner in these endeavors. We can provide guidance and support in the development of research proposals through in-kind and technology contributions, as well as helping to foster relationships with other industrial partners. Furthermore, we can provide help in skills development of your team members through training and application development support, as well as providing openings for co-op placements and internships. Well, that's a bit about us. With that in mind, let me introduce you to our guest presenter today. Dr. James Andrew Smith is an assistant lecturer and graduate attribute lead in York University's Lassonde School of Engineering, where he specializes in experiential teaching methods. His research combines aspects of robotics, biomechanics, and 3D printing to the development of dynamic human birth models and other biomedical devices. James received his BSc and MSc degrees in electrical engineering at the University of Alberta, and following the completion of his PhD in mechanical engineering at McGill University, he undertook a postdoctoral fellowship at the University of Jana's Institute for Sports Science in Jena, Germany. He has won teaching awards at Ryerson University as well as the University of Alberta. James was the recipient or co-recipient of 4 international IEEE Real-World Engineering Project Awards from 2007 to 2010. He was also the co-recipient of 2nd place in the design competition at the 2012 Healthcare Innovation Conference in Houston, Texas. James has worked on the accreditation files for multiple engineering programs, including electrical engineering at York University and biomedical engineering at Ryerson University. So with that, I'll pass this over to Dr. James Andrew Smith.
Okay. Thank you very much, Graham and Rochelle. All right, here we go. All right, so I'm just sharing the screen right here. Okay, so today I will be talking about the development of training simulators that we've been doing in our research program to improve labor induction techniques. But I wanted to start off with sort of the background behind that. A few years ago, I was working on legged robots and was faced with a dilemma of what to do if I wanted to embark on a real new research project. And a lot of us are faced with that issue when opportunities come up related to funding and possible publications and patents and that sort of thing. And that's a really good reason for undertaking new research projects. But it requires a lot of work, looking at the history of a particular research or science domain, getting up to date with the methods and conventions of that domain that might be a little bit different than what your experience is in the previous domain that you were in, and learning new tools that go along with it. And from a research perspective, that can be pretty risky because it typically means a downtime in terms of productivity, in terms of research publications, etc. And because it's different than the research you're used to, the outcomes for the work that you want to do might not be certain. And so it can be a really risky venture, but the counter to that is it can be really worthwhile as well. But what's important is that if it's a worthwhile endeavor to go after, you typically want to minimize the risk by being able to produce early results. And for an academic, this means minimizing time to new publications. And so when I undertook this research work in these training simulators for labor induction, I wanted to use a tool that would have a good graphical interface, that would provide the numerical results that I was used to getting, but also because of what is typically required in research publications is explicit access to the analytical math, the equations that underlie the system that is developed using the graphical user interface. My background was primarily, when I started this, with MATLAB and Simulink for doing legged robot research. But what I'd found was that with a lot of the review and reviewers that we were getting, there was pushback from the reviewers saying that they wanted something beyond the numerical result only papers that we were producing. And they had a number of reasons for wanting that, including things like you get different results if you use different integrators and things along those lines. So we started investigating how to use Maple and MapleSim. One of the good points about it was the graphical user interface for MapleSim is similar to what we were seeing in Simulink, so that was a plus. And we knew that because of the connection to Maple, we would be able to get that output of equations that was being demanded by the reviewers, and it was really the unique product that could allow us to do that quickly and accurately. So we needed to make sure that the results of the simulations, the mechanical simulations we were going to undertake, would give us both the numerical results we were used to and these new analytical results that we knew the reviewers were asking for. Specifically, what we were looking for was to contrast input forces for these labor induction models to produce results where we could also look at changes in shape of our model and compliance changes that were going on inside of our model. And it meant that we needed to have access to the kinematics and dynamics of the model. We needed to be able to look at the underlying forces, the rates of change, and the constraints and the constraint relationships of our models explicitly. So we found that MapleSim could yield those equations that we needed. It allowed us within our team to have really good discussions, not only of those graphs that we were producing, but what was going on in terms of those equations. We could actually look at them explicitly. So that was really, really good. And the output from Maple and MapleSim were publishable, basically almost in the form that we were getting out of the programs. So that was really good. That there was very little work that had to happen afterwards to process those equations to make them publishable. So that was really good. It helped us speed up our process to publication. Now, we hadn't started this process blind. We had used MapleSim in the past in our classroom environment. So I had used it in a third-year instrumentation class for electrical engineers because MapleSim provided a really good tool for what we refer to as inductive learning. And that's sort of the inverse of what typically happens in the classroom, which is a lecturer at the front explains all the rules, and then the students have to figure out the behaviors from those rules and those equations. Inductive learning is the opposite approach. Basically, you allow the students to self-explore, to use the graphical interface to examine what's going on in the system, And then it helps produce the equations that underlie it, even if they're complicated, to allow discussions to occur sort of in the opposite order. The students loved it, and I liked it as well because it allowed us at this third-year course to compensate for these typical feedbacks that we're getting from the students when we're trying to introduce new material. And that was, and if ever you've taught a university or college class, you'll have heard this from your students, that the underlying material hasn't been covered before, or they've forgotten how to do it, they've forgotten their calculus from 2 years before. And this inductive approach using supervised sort of production of models using MapleSim allowed us to bypass those standard sort of hiccups in the learning process. It worked so well that the students ended up using the same tools that they were getting in their instrumentation class in the control engineering class that was happening in parallel. So they were self-learning, self-directing their learning in their controls class using the same tools because they liked it so much. So we had this really good positive experience in class, and now we wanted to see what would happen on the research side. So knowing that MapleSim could, from the graphical user interface, produce these equations, basically the way it works is you draw up your model, whether it's an instrumentation amplifier or some mechanical mechanism, as a schematic, and then from there, the idea is you request through this paperclip icon the equations, and then it connects to Maple, and within Maple, then we get to extract and manipulate those equations in a form that's familiar with us. So the process is actually pretty straightforward. Now, getting back to what we were doing, the whole point of this exercise, which was to improve training models for labor induction and for midwives and obstetricians. This started when my wife and I decided to have kids, and I didn't really understand what was going to happen in the birth process. And I was having issues with understanding why medical practitioners were also reluctant to give certain predictions about how the birth outcomes would be. And so for a lot of people like myself, not going and knowing very much about birth, it can be really mysterious and scary. But it really shouldn't be, because millions of births happen every year around the world. It's a very normal process, and yet there's this air of mystery around it. And as an engineer, that sat very poorly with me. What I wanted to do was understand it better. And as an engineer, the way to better understand things typically is to build a model of it. And I realized that the fastest way to go about doing this would be through a computer model, and MapleSim was the right tool to make that happen. So we undertook the process of creating a computer model in MapleSim in the short term, and then in the long term, the idea was to use the results from those simulations to create robot models that could eventually be used for training in sort of medical scenarios in medical schools and midwifery schools and that. So how are babies born? What's going on most of the time? Well, most of the time there's no problem. Births happen, and there's typically a really smooth process. The woman goes into labor. A few hours later, the baby is born, and there's very little intervention that's required. That said, there are cases where intervention is needed. In cases of risky labor, so depending on the physiology of the woman or what's going on with the baby, sometimes the births can be a little bit riskier. They can be harder to occur. Sometimes they go beyond their 7 hours that are typical for a first birth. In some cases, women can go into labor for tens and tens of hours. And in a lot of those cases, what's going on is that the cervix, which is in the screen right here, this part right here, it's at the bottom of the uterus. So this is the uterus right here, and it's hard. To get an idea for how hard it is, if you touch the end of your nose, that's how hard the cervix typically is. The tip of your nose is how hard it is. During the birth process, when the baby is about to come out, it actually feels more like the tip of your ear. So if you pinch your ear, that's how it should feel. So what's supposed to happen in the early part of or early stage of labor is it's supposed to transition between those two. If it doesn't, if it remains hard, then the birth is blocked effectively. And then the question becomes, is surgery needed in order to get the baby out, because the baby can't get out the normal way? And in Canada, what we see is that about 30% of births end in cesarean section. And what that means effectively is the surgeon goes in and cuts open the abdomen of the woman to extract the baby. So we're effectively coming in sideways. And this is actually much higher than the recommended rate of cesarean sections as stated by the World Health Organization. It should be closer to 15%. And what we're seeing is that Canadian doctors are overly enthusiastic about cutting open their patients to get the baby out. And this can have really negative impacts on women in post-birth because they have to recover from this major surgery that they just had. And so there are alternatives, and we wanted to look at what these alternatives would be. And so traditionally the alternative to cesarean section would be induction or sort of speeding up of labor or helping of labor using either a pharmaceutical product, a drug, typically a gel that's applied manually to the cervix, or a balloon that's inserted through the cervix just under the baby's head. And this manual induction process or pharmaceutical induction process combined is about 20% of births. So what we're seeing is that a lot of births end in cesarean section. A lot of births also end in or use induction to get through. But the induction process typically is safer and it's midwife friendly, which is really good because it fits in within their typical method of practice. And midwifery is becoming a more and more common way of going through with the birth process. So we wanted to figure out what would be models that we could use to help midwives and OBs train to make this happen, because obviously there's something else that's going on here that's under the hood that's favoring more of the cesarean section approach. So what we found is that the typical models that are made right now typically are rubber blocks. They don't represent at all what a cervix or uterus looks like. They typically are very static as well. They don't represent the dynamic nature of labor, how the uterus changes, how the cervix changes. If you ask any woman who's had birth or given birth, they'll tell you that labor can move very, very quickly, and it doesn't look at all like these models that are typically used by midwives and OBs. So our thought here was that our models for training midwives and obstetricians should be just as dynamic as the physiology of the woman and the baby, that we should be able to represent how the uterus moves, that we should eventually be able to incorporate real contractions into the model, and that the cervix itself should do the cervix model should do the same things that the cervix does, which is it softens, it stretches, and believe it or not, it actually disappears about halfway through the labor process when you transition from latent labor to full active labor. And that's what we wanted to be able to see. So what happens with a balloon induction, so using a Foley catheter balloon, is that the balloon itself is inserted through the cervix right here, and the balloon appears right here, right under the amniotic sac, and that's where the baby is. And the idea is that it's then pulled downwards like that, and for reasons that are apparent to people who understand the physiology really well, by having a force that's applied to the top of the cervix, the cervix is then told, it receives a message effectively to say, you have to soften now. And what they found over time is that you can actually get the cervix to listen by having a little bit of that force applied, and it will do what you see in the bottom here, which is it will change shape, it will get thinner and thinner, and will pull away, and then eventually the balloon pops out, and then the baby can follow through afterwards. And that's what we wanted to be able to simulate in this model. So we needed to be able to model compliance, dilation, and effacement. These are the three components that are required in order to have a medically valid kind of simulation. So compliance is the softening, so going from hard to soft. Dilation is the opening sort of laterally, sideways. And effacement is the thinning out of the cervix, the disappearing of the cervix itself. What we wanted to do is model a typical induction kind of labor, so a 7-hour labor, which is typical of a first labor. And we wanted to make sure that the dilation rate was under 1 centimeter per hour, closer to about 0.7 centimeters per hour, which is typical of the latent or early stage, so the first half, so up to about 4.5 centimeters of dilation. That's typical of labor. and we were going to ignore for the time being with this model the active labor stage, where all that pushing happens and that afterwards. So we wanted to get to the early stage of labor and see what would happen with this model. And what we found is that with a model that had two pairs of spring dampers, so one at a pin joint and one at a prismatic joint, and then basically we had two sort of prismatic joints and two pin joints in there. What we found was that with a little bit of feedback, we could get a pin joint spring version of this, so only one sort of spring joint pair, to track the dilation rate accurately and smoothly. So that effectively what we ended up getting was after the onset of simulated labor, that we would get a straight line horizontal tracking of dilation speed, showing that it is smoothly progressing. So that's representative of what we would typically see in labor. And so that was really important that we would get a model that could do that. The other thing that was really important was that we know that some other researchers have been doing the same sort of thing using finite element analysis models of the uterus, modeling it as a container, basically a vessel. And that's a very computationally intensive sort of modeling, and it works really well in the research environment. But if we want models, computer models that could be, say, run on a cell phone or for a midwife or something like that, we want something that's not computationally intensive, like a finite element analysis model. So by going to this sort of linkage and spring-based kind of model, this is a much more computationally efficient kind of model, one that can be adapted to the current circumstances that is being seen by a midwife or an obstetrician on a mobile device, for instance. So the next thing we needed to do after that was to move from the computer-based simulation to robot models. And so with my graduate students, we ended up working on 3D printed versions of the cervix and the uterus to make dynamic robot models that could be touched in real life. One of the other ingredients that we had to plug into this was effectively we needed to get hands-on experience with real cervixes and uteruses. So we collaborated with some fabulous people at McMaster's Department of Obstetrics and Gynecology through their pathology lab. We worked with Dr. Derek Lobb to look at post-hysterectomy uteruses, and that's what you see up here, a scanned version of one. And we used that to 3D print, right down here, uteruses and to test, while we're in the pathology lab, how compliant the cervix and the uterus was or were. And so we were able to get a realistic impression for what's really going on with the uterus. And that helps us inform our computer and robot models. And this is one of the robot models that we've sort of developed. And so what you see here is a representation right here of the cervix. Inside, what we have is a simulation of the induction balloon. There's a force that's pulled downwards like that, and then the material that's here, this latex material, has a granular material inside that can demonstrate variable compliance through the action of removing air. And so this worked as well. We were able to demonstrate that we could get people to palpate, that is to touch the outside surface here and determine while blindfolded whether the material was soft or hard, as they would with a real cervix. Where are we going next with this? Well, we are doing a number of things. One of the things that we need to now incorporate into our model is the fact that when women go into labor and they give birth, they actually give birth at different angles. Sometimes they're doing it lying on their backs. Sometimes it's in a different position. And as they move from one position to another, the cervix position changes direction. And the forces on it change as a result of that. And so we now need to move to a more three-dimensional kind of model that can incorporate these three-dimensional forces that are being applied based on the position the woman finds herself in during labor. One of the other things that we're doing is we're also exploring different materials, different soft materials to represent the cervix. So what we have here are idealized versions of the cervix. So this one right here was printed with thermoplastic urethane on a NinjaFlex material on a Lulzbot printer. and that gives us slightly harder results than we want. We're now looking at other materials from companies like Stratasys and silicone 3D printed materials as well that can be used to replace that original red model that you see right there. We're also looking at creating robot models that combine both compliance and dilation in one. In the past, what we've done is either a dilation model or a compliance model, and now we need to be able to combine both and to bring effacement into that as well. We are doing extensions of this work into other domains as well, and we've worked with a local clothing company here in Toronto called Nixwear to develop clothing testing robots that incorporate both hard motion components and soft compliant components as well. And so we're looking at extending our results into that direction. So in conclusion, what I hope came across is that we're able to engage in a new research direction, looking at training models for labor induction, and we're able to use MapleSim especially in the early stages to get results out the door quickly to make sure that we were continuing the publication directions that we needed to do and to get at, and we will be using it to continue the research looking at other areas of our cervix model and our uterus model. MapleSim has been really, really good at being incorporated into the typical engineering design workflow that we have. It's been incorporated into a biomechanics robotics application, and we've extended it now into these soft robotic biomedical models that are sort of a new trend in the robotics industry. These soft robotics things are really taking off now. And so what we've seen is that MapleSim itself has permitted us to do rapid model prototyping, which is super important in engineering. It allows us to combine both mechanical and electrical and other domains together. We get the standard numerical simulations that we all know and love, and it allows us to do extra things like extracting those dynamics equations to ensure that we have better discussions about the models and to create publications that are reviewer friendly. And there you go. That's a summary of that we've been doing.
Well, thank you so much, James. And what I'd like to do is just share my screen here for you, and we'll take you back to just wrap this up here. You just bear with me for a minute.
Okay.
Lovely. Thanks for bearing with me there. So thanks a lot again. And just to wrap up, I wanted to provide just a bit of an introduction to the tools that were used in James's project. So he's talked about them a bit already, but MapleSim is our tool for multi-domain system-level simulation. And it allows you to quickly build models of complex dynamic systems by selecting and connecting components from a large library of pre-built components, covering domains like mechanical, multi-body, control, thermal, and a wide variety more. We also offer specialized libraries for batteries, drivelines and transmissions, advanced hydraulics, and pneumatics. It's important to note that unlike traditional tools like Simulink, connections between components in MapleSim represent physical connections that are acausal and not just signals flowing in only one direction. So this simplifies the modeling task, and it reduces the complexity of the resulting block diagram. And of course, in our environment, you can combine them both. You've got that option. Maple, on the other hand, is our environment for calculation management and design exploration. It allows you to go beyond the simulation and get deeper insight into your designs. These two softwares work together in a very sort of lockstep way. There's thousands of mathematical functions that are ready to tackle problems like parameter tuning, optimization, Monte Carlo analysis, and the list goes on. And because at the core of Maple and MapleSim is a powerful engine for symbolic computing, you're able to extract system equations, compute symbolic Jacobians, and get analytical solutions for inverse kinematics and dynamics. The document interface as well allows you to easily capture every step you take, and the resulting interactive documents, they're easy to share, review, validate, and reuse through your product design. The documents can even be shared on a central server, and they're going to be fully interactive within a web browser. And a full programming language will allow you to script and automate analysis tasks, so you can really take things about as deep as you'd like them. So together, these are some powerful tools that we have, and they really help enable a model-driven process in whatever sort of research or projects that you're working on. And internally, we have a lot of expertise in system-level modeling and design validation. We've worked with dozens of engineering research organizations to help them take advantage of state-of-the-art techniques and tools to allow them to deal with growing complexity and to succeed in their research goals. So we offer a variety of engineering solution services really to help make your engineering project succeed. They'll allow you to achieve more in less time, and will really help you sort of hit the ground running and make sure that you've got the skills you need to make sure that your return on investment will be quick.